Hello, thank you all for listening to my presentation. Myself Bibhu and I am a PhD student at the University of Freiburg, Germany. As the title suggests, we are proposing a method to measure temperature passively through a metal wall which can be adaptable for a hermetic metal container. Communicating with sensors through a sealed metal container is difficult as wired methods can compromise the structural integrity of the system. Another challenge is the harsh environment, as most standard semiconductors can only operate up to 125 degrees Celsius. Further, RF shielding effect makes things difficult to communicate as thick metal walls are not transparent to electromagnetic waves. So to address these challenges, we propose an ultrasonic temperature measurement system where a 20 mm thick aluminum wall is used, mimicking a sealed hermetic metal container. A PGT transducer is coupled to the outer side to generate and receive ultrasonic wave burst. A sensor element made from brass is coaxially coupled to the other side. In an ideal case, there will be two reflections, one at the aluminum brass interface and another one at the brass air interface. By measuring these two reflections, we can calculate the acoustic speed in brass. However, due to reflections at the aluminum and PGT interface, multiple unwanted echoes will be generated, which needs to be suppressed. So the back reflected waves at the aluminum PGT interface causes multiple unwanted echoes. At the aluminum PGT interface, part of the ultrasonic energy is observed and part of it is reflected due to acoustic impedance mismatch. So to solve this problem, we modeled our PGT as a receiver and we calculated the zero reflection loads numerically using the KLM model to minimize the back reflected ultrasonic wave, which leads to a suppression of unwanted echoes, also a higher sensitivity of the wanted reflections. The evaluated zero reflection loads can be found in the poster. As we see, the unwanted reflections were reduced by 75% with zero reflection loading. The three echoes are shown in matching colors. Now we attach a sensor element coaxially to the other side of the aluminum wall and do a pulse echo measurement to calculate the time of flight in the sensor element. By measuring the time of flight, acoustic speed in the sensor element can be calculated using this equation. This figure shows the calibration results of the brass sensor element. We saw a linear dependency in acoustic speed and temperature, which follows the following equation. Since our sensor has a higher thermal mass, we measured the response time of the sensor from room temperature 27 degrees Celsius to 40 degrees and compare it with a commercial thermistor. The response time is not optimal, but it should not be a problem in a long-term measurement system. Further, the thermal mass of the sensor can be tuned based on the system's requirement. And as a conclusion, we have presented an ultrasonic temperature measurement system adaptable for a sealed metal container without interfering with the system's structural integrity. We achieved a precision of 2 degrees Celsius and a resolution of 1 degree Celsius. The sensor element itself is robust and can be subjected to harsh environment. The sensor, the PGT transducer, and the complementary hardware are very cost effective. Thank you for listening to my presentation.